A damped spring constrained to move in one direction, such as might be found in a railway buffer, is subjected to an impulse of duration 5 seconds. The spring constant divided by the mass causing the impulse is 10 m to the minus 2 s to the minus 2, and the frictional force divided by this mass is 2 m to the minus 2 s to the minus 2. Let's look at a mass on this spring. Here I'm showing its position vector x. 0 is the equilibrium position that the mass might have. By Hooke's law, we have the restoring force minus kx. So that vector points in the opposite direction to x. The magnitude of the restoring force is proportional to the displacement x. So if we double the displacement, we double the magnitude of the restoring force. So k is some positive constant here. It's called a spring constant. Now let's suppose that the velocity of the mass is to the left in this picture. So the velocity vector would look like this. It's dx dt. We will assume that the friction force is proportional to the speed of the mass. So the speed is the magnitude of the velocity. It's the magnitude of dx dt. And let's suppose the proportionality constant is c. So c is some positive number. So we stick a minus sign in front of this to indicate that the friction force is in a direction that is opposite to the velocity vector. The velocity vector is dx dt. So if dx dt points to the left, the friction force will point to the right, opposing the motion. Now, if we ignore the impulse, then Newton's second law tells us that the resultant force on the mass, that is the mass times its acceleration, is the sum of just these two forces. So the force vectors are minus k times x and minus c times dx dt. Now let's suppose that we have an external force which I will call F. F could be positive or negative. If F is acting in this direction, then it's positive. If F is acting in this direction, it is negative. We can now write our differential equation like this. Divide everything by m, and I've brought over these two terms. Now we're given that the spring constant divided by the mass causing the impulse is 10. K is the spring constant, so K divided by m is 10. The frictional force divided by the mass is 2. By the frictional force we mean the constant in this expression here for the frictional force. The constant is c. So c divided by m is 2. Now we are dealing with an impulse in this example. So let's see what an impulse is. Well, if a force, say f of t, acts for a certain time, the impulse imparted by that force is got by integrating this force over the time interval for which it acts. So if it acts for a time interval from A to B, then this here is the impulse imparted by the force over that time interval. So suppose our force function looks like this. Then the impulse over the time interval AB is just this area here. Now we will deal with a force that is constant, so we don't even have to perform an integral. So in our situation we will be dealing with a constant force, which I will call F, and it's acting over, say, time interval A to B. So we just have the area of this rectangle. Now in the example that we are doing, it turns out that F divided by m is a box function from t equals 0 to t equals 5, or a rectangular function if you like. To get that function, we take u of t, the unit impulse, and subtract u of t minus 5. So we're dealing with a unit step function here actually. That's the situation in this example. So u of t is 1 for t greater than 0, and if we subtract ut minus 5, which is 1 for t greater than 5, then this part here cancels out this part here for t greater than 5, so we get 0. But for values of t between 0 and 5, we just have 1 minus 0. 1 minus 0, which is, we get 1 for this interval here. And for values of t less than 0, we will of course get 0. We just have 0 minus 0. We are given that the system starts from rest, so the value of x at 0 is equal to the derivative of x at 0, or the speed of the system at 0, which is 0. Now let's solve this differential equation. We take the Laplace transform of the differential equation. We have the Laplace transform of the second derivative. We covered that before. You can look that up. We have twice L of the first derivative, so here is L of the first derivative. We have 10 times L of x. Now we could write L of x as capital X of s, or what's done here is to write L of x as x bar. So remember, we're looking for little x as a function of time. That's the solution to the differential equation. So L of x is given the notation x bar here. Now we need to get L of u of t. We can just look that up. Here it is 1 over s. Now what about L of u of t minus 5? Now here we can see that the time has been shifted by 5 units. So that involves the second shift theorem. Here is the second shift theorem for a general function little f. But we can make little f here equal to u. So we can replace f with u, and this is what we get. But if we multiply u of t minus a by u of t minus a, we just get u of t minus a. It's a unit step function where the step occurs at t equals a. So if we have two of these functions and if we multiply them together, we just get the same back because the height is 1. So we just get 0 times 0 here, which is 0, and we get 1 times 1 here, which is 1. So the product of these functions is just u of t minus a. And we can see here that the result is going to be e to the minus sa times big F of s, where big F of s is the Laplace transform of little f of t. But little f in this case is u. So little f of t is u of t, and we looked that up already. We know that from the table that that's 1 over s. So in our example, a is equal to 5. So if this is 5, we just have e to the minus s times 5, or minus 5s, times big F of s, which is 1 over s. I can write the 1 over s in front here. Now, we have set x of 0 equal to 0, and since the system is starting from rest, we have the derivative x prime is 0, 0. So these two terms go out, and this term over here goes out. We need to isolate x bar of s. X bar of s is the Laplace transform of x of t. So there are three terms here: s squared x bar of s, 2s x bar of s, and 10x bar of s. Isolate them, and everything else on the left hand side is actually 0, so we get that factorize out x bar of s, divided across by the quadratic s squared plus 2s plus 10. Next we get the partial fractions of this expression here. So one of the fractions has a quadratic denominator, so the numerator is a linear function of s. It's got the form as plus b, where a and b are constants. The other factor in the denominator is linear, so the numerator is just a constant. So if we add these two fractions together, we get this here. So as before, we multiply like this. Now the numerator must equal 1, because we've 1 times 1 is 1 up here. So the s squared terms must be 0. So a plus c must be 0. The s terms must be 0 also. So b plus 2c equals 0. And finally the constant term, which is 10c, that must equal 1. So c equals 1/10. Since a plus c is 0, we see that a must equal minus 1/10. We see that b is equal to minus 2c from this equation, so that's minus 2/10. C over S is written down first here, where C is 1/10. So we've 1/10 times 1 over S. 1/10 over S, or 1/10 times 1 over S. Then this fraction is written down second. A is minus 1/10. B is minus 2/10. Now the minus 1/10 has been pulled out of the top here. And if we do that, we're left with plus S plus 2 on top. So up here we have minus 1/10 S plus 2/10. Take out the minus 1/10, and we've minus 1/10 into S plus 2. Now the denominator of this fraction cannot be factorized, so we can complete the square here and get it into a form that we can read from a table. So we have the coefficient of S to get 1, so we write S plus 1 squared here. If we square that out, we get S squared plus 2S plus 1. But we want to get 10, so we have to add on 9. 1 and 9 gives us the 10. Now I just want to look at this fraction in more detail. We're going to be using both of these transforms here. So in the denominator here we have something of the form S squared plus A squared. S squared plus A squared, where A is 3. But you see we need S on top. So to get it into this form here, we have to have S plus 1 on top. So it's the same as what's inside the brackets here. The S's are the same. We will use the shift theorem then to deal with the plus 1. Or we can actually just look it up here. The shifted forms are also listed in this table. So we need to turn S plus 2 into S plus 1. Well, to do that we can write the 2 here as 1 plus 1. And then we can take S plus 1 over this denominator for this fraction, and then take the plus 1 over the denominator for the second fraction. So to add these two fractions, we just add the numerators since the denominators are the same, and we'll get back to this. Now you see we have a constant on top here, so we want something of the form constant over S squared plus A squared. And that constant on top better be the square root of the constant underneath. So we can see that A squared is 3 squared. So A is 3. If we compare to this here, we will use the shift theorem later to deal with the fact that we have S plus 1 instead of S. But anyway, just to deal with A, we have 3 squared underneath, so we need to have 3 on top. So we need to change this 1 into a 3. If we stick a 3 up there, of course we have to stick a 1/3 in front of this fraction. So now we're ready to get the inverse transforms of these two fractions. But before we do that, we're going to multiply by 1 minus e to the minus 5s. We also have the minus 1/10 here, which is multiplied by each of these. So we've minus 1/10 times this fraction, and we've minus 1/10 times plus 1/3. That gives us minus 1 over 30 here. So we multiply 1 by all of this, we get it back of course, and then we have minus e to the minus 5 taken in through the square bracket here. And we can use one of the shift theorems to deal with these terms, because these terms involve the term e to the minus as, where a is 5. Let's look at the inverse transform of 1 over 10 times 1 over s. Well, we can get that from a table of transforms. We've seen this already. The inverse transform of 1 over s is u of t, the unit step function. So the value of this function is 1 for positive t. So we're just going to get a 1 here, and by linearity we take out the 1/10, so we have 1/10 times 1. So we're only dealing with positive t here, so we can just write down 1 here. Now the next term has the form s over s squared plus 3 squared, as we discussed already. The constant in the denominator is 3 squared. So if it was just s over s squared plus 3 squared, the answer would be cos 3t. But you see s has been shifted by 1. So we have to use the first shift theorem to deal with this. So as a reminder, here is the first shift theorem. So here we have a function of s plus a, where a in this case is 1. A is not 3 now. This a represents something different. It represents the shift here rather than the constant in the denominator. So we see that the inverse transform of it is e to the minus at times the inverse transform of big F of s. Well, we know that that's just cos 3t. Big F of s is just s over s squared plus 3 squared, and its inverse transform is cos 3t. And we have to multiply that by e to the minus at, where a is the shift. So the shift is plus 1, so we have e to the minus 1t here. Now let's look at the next term. we have something of the form 3 over s squared plus 3 squared. So, as we've discussed already, we got it into this form because we have it listed here. A, in this case, as you can see, is 3. So we're going to get sine 3t. So here's the A. The shift is plus 1, so we have to use the first shift term. So here our term has the form f of s plus 1, where f of s is 3 over s squared plus 3 squared, and the inverse transform of f of s is sine of 3t. That's little f of t, but we have to multiply by e to the minus at, where a is the shift, a is plus 1. Again, this a is different from the a referring to the constant in this, referring to the 3 squared. A here is the shift, so we've a to the minus 1t now. Now the next term has an exponential in it, and that suggests use of the second shift term. We see the exponential appearing here. For this term here, the power is minus 5s, so a is going to be 5. So we're going to have something of the form little f of t minus 5 times u of t minus 5. Well, little f is the inverse transform of big F of s, where big F of s in this case is what's in front of the exponential term. It's 1 over s. And we know that the inverse transform of 1 over s is u of t. We got that from our table of transforms. But we actually want u of t minus a, where a is 5. So as a reminder, here it is again, the inverse transform of 1 over s is u of t. But from the second shift term, we want u of t minus a. Forget this u minus t of a, this always appears. So in this case, little f happens to be u, and we always multiply by u of t minus a, regardless of what little f is. So we'll have u of t minus 5 multiplied by u of t minus 5. But if we multiply two unit step functions together that are identical, we just get that unit step function, as we've seen already, because the unit step function is equal to 1 for values of t greater than a. And if we multiply 1 by 1, we just get 1. So u of t minus a times u of t minus a is just u of t minus a, where a is 5 in this case. Now let's get on to the next term. Now, the next term is identical to a previous term that we looked at. It's identical to this one here, except for the exponential, e to the minus 5s. And we got the inverse transform of this before. We saw that it's e to the minus t cos 3t. But we use the second shift theorem to deal with the fact that we're multiplying by the exponential. In other words, we know what little f of t is. It's the inverse transform of big F of s. That's this term here without the exponential. We know that that's e to the minus t cos 3t, but we have to get little f of t minus a, where a is the power here, which is 5. So we look to this term here, e to the minus t cos of 3t, and replace t with t minus 5. So we just take the t in this and replace it with t minus 5. And we'll have cos of 3 times t minus 5 here, and then we have to multiply by u of t minus 5. We do something similar for the next term. The next term is this here, and we got the inverse transform of 3 over s plus 1 squared plus 3 squared already. Just this fraction part here, we know it's e to the minus t sine 3t, but because it's multiplied by the exponential, e to the minus sa, where a is 5, the inverse transform will be little f of t minus a, where little f of t is e to the minus t sine 3t. So we replace the t with t minus 5. We get e to the minus bracket t minus 5 sine of 3 bracket t minus 5, and then we multiply by u of t minus 5. So we just used these two results to give us these new results.